So there is this cycle, and this cycle is somewhat problematic because we cannot find a closed form solution due to that cycle. But instead of worrying about this cycle, there is actually a pretty brilliant idea, because we can simply actively use this cycle instead of worrying about it. What do I mean by actively using this cycle? Well, there are these two quantities, the responsibilities and the parameters theta. Now, we can fix one, say the responsibilities, and then we simply optimize for the other one. And that gives us a new iterate of parameters, which allows us to update the responsibilities because the parameters have changed and they depend on the thetas. And then we can iterate this cycle a couple of times and always update our parameters. Now, there's an obvious problem with that. These responsibilities at any time step are not the maximum likelihood posterior values, so the maximum likelihood responsibilities, which would be the responsibilities if we insert the maximum likelihood parameters. But our hope would actually be that if we iterate long enough, these parameters, and with these parameters the responsibilities, would actually converge to the maximum likelihood values. Okay, this is going to be tough to show. But a first approach to showing that would be to show that these two steps, so we have two steps, the optimization and the update, none of these two steps actually makes things worse. We will define what this means, making things worse. But if none of these steps makes things worse, then we eventually must hit a ceiling, because there is an optimal value. So we're bounded from above, and we will approach this optimal value if we don't destroy anything within one of these two steps. Okay, that's what we'll try to show as a first step. And in order to analyze this problem, in order to show that, we make actually fewer assumptions than we do right now. So right now, these responsibilities, they are the true posterior distribution of the current theta, okay? But we're going to assume less structure here. We're going to assume that we just have an oracle wherever we get this oracle from. And this oracle is a distribution over the latent factors. And this doesn't impose any structure on them. And this will actually be beneficial to our analysis. Okay. So with the help of this oracle Q, something very, very interesting happens. And it's a bit theoretical, and it looks a bit complicated, but it's actually not. And I strongly recommend you to really look at each step and try to understand this, because this is the very foundation of variational Bayes. And it's also crucial to understand the expectation maximization algorithm and to understand the variational autoencoder. So let's walk through it one step at a time. We start off with the likelihood, or the log likelihood. And now we do a very clever trick. We insert two ones. Okay, so far nothing much has changed. But the clever thing is, of course, to replace these ones with appropriate other terms. And the first one is to replace this first one with the integral over this density QZ, and because it's an integral over a density, it integrates to 1. And you recognize this one here. So this is the integral over QZ and integrating out Z. And because this logarithm of P of X is independent of Z, we can just pull it into the integral. It's a constant with respect to Z. And that's exactly this one up here. Now you can also already recognize the second one. The second one is just the fraction QZ over QZ, and that's obviously 1. And that's what you can recognize here. Okay, so the only thing that improved is that we introduced the oracle, but this doesn't look any simpler. But now we can do some reformulations. And the first reformulation is this identity. namely that the marginal distribution is the same as the joint distribution over the posterior distribution. How can you see that? Well, just multiply this identity by the posterior, and on the left-hand side you have the multiplication law, and on the right-hand side you have the joint distribution. Okay. And you can recognize this identity by looking at the second line, okay? So in the first line we had this marginal, and in the second line we have the joint and the posterior, and you can do the math yourself, but it's just an application of linearity of the integral and also the logarithm rules which apply because we have a fraction here, which is a division. Okay. Now, this still doesn't look much simpler. In fact, it looks more complicated. But now we have two summons, and each of these summons has a very distinct role and a very distinct meaning. And we will have a look at both of them individually. And we will start off with the second one. If you look at the second one, you will recognize that it's a very special integral. Namely, it's the Kullback-Leibel divergence, or KL divergence, between the distribution Q and the posterior distribution. And you may recall that the KL divergence is some kind of similarity measure between the two distributions. It's not really a distance measure, it's not really a metric, because it, for example, fails to be symmetric, but it's non-negative, and it's also zero if and only if the two distributions coincide, at least almost surely. Okay, so that's interesting, because this posterior is the inference distribution we're interested in, and all of a sudden there shows up a term that measures the distance between our oracle distribution and this true posterior distribution. Okay, that's interesting to keep in mind. Now, we said that this KL divergence is non-negative. Now, the thing is that this log likelihood is constant with respect to Q, with respect to our oracle. No matter what we choose as an oracle, this log likelihood remains unchanged. Okay. Now, that means that 1 needs to be lower or equal in value than the log likelihood. Why is that? Well, no matter how we change Q, the log likelihood stays the same. And in order to get from 1 to the log likelihood, we need to add 2. And 2 is the KL divergence, which is non-negative. So we need to add something non-negative to get to the log likelihood. And that implies that this term 1, this integral 1, is lower or equal than the log likelihood. Okay. Well, what is this term 1? What is this other strange integral? Well, once again, we can apply the logarithm rules. And what we end up with is a bit of a strange expectation, but we will dive into that a little later, plus the entropy. The entropy is just the integral of qz times minus logarithm of qz. That's the entropy. Okay. And in the literature, this term number 1 has a very distinct name. It's called the evidence lower bound. Okay, why is that? Well, first of all, the evidence lower bound is a function of our oracle Q and the parameters theta. Okay. Now, it's a lower bound due to this fact that I just told you. It's lower than the evidence, lower than the log likelihood of the data, which is sometimes also called evidence. That's why it's called the evidence lower bound, or short elbow. And it has various other names. It's sometimes also called variational lower bound. Or in physics, it's sometimes also referred to as free energy, or also variational free energy. And this variational lower bound, by the fact that it has so many different names and so many different application areas, you can already tell that it's very important. And in the next slides, we will see why the evidence lower bound is so important and also so nice when it comes to inference in latent variable models. So remember that when we introduced this distribution Q, it was supposed to mimic the posterior distribution, the inference distribution. And one way of quantifying this ability to mimic the posterior distribution is to look at the KL divergence and to see how much Q deviates from the posterior in this KL divergence. And now this is a function of the function Q, and we're trying to optimize this KL divergence with respect to Q, and whenever you optimize with respect to a function, this is called a variational approach. And that's also why the evidence lower bound is sometimes referred to as the variational lower bound or the variational free energy. Now, from the theory from the previous slide, we can further deduce a very, very important observation. On the previous slide, we have established this equation here that tells you that the log likelihood of the data, the left-hand side, can be decomposed into two summands, namely the evidence lower bound or variation lower bound, and exactly this KL divergence we've seen up here, the KL divergence between the oracle and the posterior distribution. Okay, and from this equation, it immediately follows that when you're doing this optimization up here, that is finding the Q that optimally mimics the posterior, you're implicitly doing a maximization of the evidence lower bound with respect to its first argument Q. Okay. Now, why is that the case? Well, the left-hand side of this equation is constant with respect to Q, okay? So this is a C, some C. We don't know this C, but it's a constant. Now, suppose we had found the optimal Q for the KL divergence, okay? And now suppose that the evidence lower bound wasn't optimally maximized. That is, we could find a new Q prime such that we could increase the elbow by an epsilon. But now this left-hand side is constant with respect to Q, so no matter what Q I'm inserting, the right-hand side has to be in equilibrium. It has to have the same value C if you sum up these two summands. That means if I increase the elbow by an epsilon, that means immediately that I need to decrease the KL divergence by some epsilon too. And that means it cannot be, it couldn't have been the optimal Q in the first place. So that proves this second equation, this argmin equals argmax argument. And also because the KL divergence is non-negative, this also prevents that something like a plus infinity plus minus infinity equals C situation comes up, okay? So that's just a minor argument. Okay, but that's very, very interesting. Why is that interesting? Well, we would like to do this KL minimization because sometimes this posterior is hard to find. And we would like to find a Q that approximates it well. And the KL divergence is a nice way of formalizing that. Now the problem is, if we don't know the posterior, we cannot evaluate this KL divergence. But now we've proven that instead of doing this minimization on the KL divergence, we can just as well do maximization on the evidence lower bound. And that's quite fascinating. And on the next slides, we will also see that this is much easier in the cases where we don't know the posterior distribution. We can choose whether we want to do minimization or maximization depending on the situation or on the models that we're employing. And one more thing is that we have found an interpretation for the gap between the lower bound and the log likelihood. So we have found this evidence lower bound, and lower bounds are always good to estimate something, but there's always the question of what is this gap between the real value we're trying to proxy with this lower bound and the actual lower bound. And in this case, we have a very distinct, very hard interpretation, which is exactly this KL divergence. Now, you might say that this is a nice theoretical insight, but why should we really take this detour? Well, now consider again the example we started off with. We had this mixture of Gaussian on the MNIST dataset, and we found that there's this two-step cycle that might be a good idea when we're trying to do maximum likelihood estimation. And then we said, okay, we don't really know what this two-step cycle does, but maybe we can show that none of these steps in the cycle decreases the result. And now let's just look at what happens. We defined the responsibilities, that is one of the two steps, calculating the responsibilities, we defined it to be equal to the posterior value. And the important thing here is we fixed this parameter set theta t. Okay, so the responsibilities are defined as this posterior value. Now with a fixed theta t, this is by definition the optimal solution to this KL minimization problem. Okay? This KL minimization problem is optimally solved when Q is the posterior, and in this case we defined Q exactly as the posterior, so this KL is 0 and it can't be lower than 0, so this is trivially optimal. But now the previous slide tells you that this also means that this is optimal for the evidence lower bound when we're maximizing with respect to its first component. Okay? So these responsibilities inserted for Q for a fixed theta t is also optimal. Now what does this mean? This means that one of the steps in our cycle, one of these two steps, namely the update of the responsibilities, does coordinate ascent of the evidence lower bound with respect to its first argument with respect to Q. Now this is trivial because it happened by definition. We just defined this step to be this way. But it gives rise to a very, very simple idea, and that is, let's just look at the second coordinate. Let's keep the Q fixed and see what happens when we maximize theta. And maybe the second step will just fall out, and that's exactly what will happen. And that's why the evidence lower bound is such a powerful tool to analyze this algorithm that we derived. Okay, so let's look at it straight away. Let's look at the evidence lower bound and now fix Q and optimize with respect to theta. So remember previously here we had Q, we were maximizing with respect to this oracle, and now we're maximizing with respect to the parameters theta. And then we simply insert the definition from 2 slides previously. And we see that there's this entropy term in there, this h of Q. And if you look at it closely, you observe that the entropy is constant with respect to the parameters. It only depends on the first argument, only on the oracle. So since we're trying to find the optimal theta only, this doesn't matter at all. And then looking at this last line, we see that this is exactly what the second step should be doing, or what we were planning it to do. Why? Let's look at it. We have this joint model. Remember, we're trying to do maximum likelihood on this distribution. Okay, but we cannot assess this distribution. And what we did in order to cope with that was we introduced this z. But the data for z was missing. So what we're doing here right now is we're trying to maximize this log likelihood of the joint model with respect to x and z. And because the z is missing, we're inserting the knowledge about z that we have, that is our current oracle Q. So this is kind of a proxy for the quantity that we're actually trying to optimize. And this way you can say this is exactly what you should define the second step to do, because this is the closest you can get to the quantity you actually want to have. So that was a deep dive into theory. So let's take a step back now and look at what we actually did. We had this latent variable model, which we introduced because we found that our standard models are not powerful enough for these tasks, such as the MNIST dataset. But we found that we were also missing data, and that our intuitive or that our natural approaches don't work anymore. So in our desperation, we had this intuitive approach, which was this cycle. And in this cycle, we would fix responsibilities and optimize for theta, and then in turn fix the theta and update the responsibilities, and we would iterate this a couple of times. And we were hoping that something reasonable was happening. And then we sort of to show that we were actually doing something reasonable, and we found out that the cycle was actually doing alternating coordinate descent on this evidence lower bound, which is a lower bound to the evidence, which is itself again bounded by the maximum likelihood estimate of the parameters on the data. Okay, so that's a lot of nice properties, but there are also other nice properties. Because we're doing coordinate ascent, this means that our evidence lower bound with increasing optimization time is always increasing. It increases monotonically. Now, it's always getting bigger, but it's bounded by a constant. This maximum likelihood here is a constant, both with respect to theta and with respect to q. This quantity here does not depend on theta, and it doesn't depend on q. So we're always increasing, but we're also bounded from above, so that means we need to converge to something. Unfortunately, it doesn't mean we need to converge to the maximum likelihood solution, but we're guaranteed to converge, and that's also a very nice property of our algorithm. And also, it is fairly straightforward to see that if we reach the global optimum, that is, if we don't get stuck in a local optimum, then we actually have the maximum likelihood estimate of our parameters theta. And of course, something with so many nice properties, an algorithm with so many nice properties needs a name. And this name is expectation maximization algorithm. And the expectation maximization algorithm consists of exactly these two steps, the expectation step and the maximization step. And we're doing exactly what we came up with on the previous slides. And the maximization step is the maximization with respect to the parameters and fixed q. And in the expectation step, we're doing this update of responsibilities. Now, you may recall that this was also a maximization, a coordinate ascent in the evidence lower bound. So why is this not also a maximization step? Well, I would argue that this has historical reasons, and that's because this particular maximization can sometimes be solved in closed form, and this sometimes is whenever you have the posterior available. And that's the case, for example, also for the Gaussian mixture models. And in these cases, this maximization is trivial, and it merely reduces to computing this expectation with respect to your Q. And that's why it's called the expectation step. And for example, for Gaussian mixture models, this expectation reduces to the sum over all samples and the sum over all classes, and the respective responsibilities for this sample and class evaluated at the current parameter set. And now we just take this log likelihood, and this log likelihood is now the likelihood of the respective class. And that's just mixture weight times Gaussian density at sample xn given the parameters for class K. And this logarithm applies to all of these. One aspect when concerned with EM that people typically struggle with is this concept of lower bound optimization. Okay, so we set out to maximize the data log likelihood, but we found that we cannot directly optimize it, so we found a proxy to it, which is this evidence lower bound, which is really a lower bound to the quantity we actually want to optimize. Now, how does it work to optimize the data log likelihood via a proxy? Well, you find something that is always lower than the actual quantity, and then you maximize this proxy. And you start off here with this green. With this green one, it's fitted to the curve, and it's always below the curve. And then you wander up to this parabola, highest point of this parabola here, and then you fit the curve again to the actual function. So you move to this pink parabola, and then you optimize this parabola again, and you move up a little bit. And by doing this iterative lower bound optimization, you're slowly approaching the optimum of the global function, the data log likelihood up here. Okay. Something I have to stress here is this figure is forged in the sense that it doesn't show any real log likelihoods. It's just to show the point of what you're doing when you're doing lower bound optimization. One thing that is really very important is that because we're optimizing a proxy, there are some things that can go wrong, and that's depicted on the right-hand side. Namely, we're starting off on the wrong side of this valley here. So we're starting on the right-hand side of this valley, and what we're doing is we're slowly going up the wrong side of this valley. And we end up in an optimum. We converge to this optimum eventually, but it's a local optimum. And that's what can happen with the EM algorithm too. And that means that initialization matters, and there's no better way than trying multiple initializations. There are, of course, more clever ways to initialize, but typically you just have to try multiple times and see if you come up with different solutions and then select the best one. Now, on to some closing remarks on the EM algorithm. It has definitely a lot of nice features. So the most prominent one, of course, is that it actually enables us to do maximum likelihood estimation on models where there's no closed form solution, like with the Gaussian mixture model we saw on our MNIST dataset. And we have guaranteed convergence. It's not necessarily global optimality that is guaranteed, but still there are a lot of nice convergence properties. But there are also issues. And we've seen that on the previous slide. We can have bad local minima. How do we avoid them? How do we do multiple restarts? How many do we do? How do we initialize our restarts? How do we choose hyperparameters? For example, with the Gaussian mixture models, we have to set the number of components. And there we can easily run into all these problems that we've seen throughout this course, such as overfitting to data, having too many components, underfitting to data, having too few components. And these are issues you have to mind when applying EM. But still, EM up to this day, and for machine learning standards, is a fairly old algorithm. It's still one of the most popular ones and the most widely applicable and applied algorithms. You should definitely know it when you want to go out in the field. Now, for the rest of this slide deck, for the rest of this lecture, we will deal with one more issue that the EM algorithm has. So for the Gaussian mixture model, it was very convenient that the posterior was explicitly known. You can derive the posterior for the Gaussian mixture model with the help of Bayes' rule fairly easily. Now the question is, what if this posterior is not known explicitly? How do we do the E step? And also, what if we have a lot of data, because then EM gets to its limits pretty quickly.